Club. Today's one would be on vitrification, thermodynamics. So if you're curious about physical aspects, this is the place to come. Dr. Wowk has a really strong history in vitrification, where he has great work, and then ice blockers, for example, dielectric heating is another one of his notable contributions, and it keeps going on. So we have a pleasure to hear from him today directly on this Meet the Author series. So we're thankful, and let's dive into it. It is like any other journal club, so we'll go through figures and tables informally. Just open your mic, give your thoughts, discussion, questions throughout the next hour. So thank you. Stage is yours, Dr. Wowk.
Thank you very much, and thank you for your kind invitation today. So I don't want this to be a talk, so please interrupt at any time with any questions or comments. We'll start with figure 1, which is a phase diagram for glycerol. I don't think I sourced it in this paper, but I think I got it out of an old issue of Biodynamica. My colleague Greg Fay has like a complete set of it, and Biodynamica was the original journal of cryobiology started by Father Basil Louyer that preceded the journal Cryobiology that the Society now produces. So there's lots of stuff going back in there as far as the mid 20th century and so on.
ICYR has digitized it, so we have digital copies.
Yeah.
If you ever need
Oh,
them.
good. Hey, is that online anywhere?
We're working on it, so it's going to go in the Cryo Museum. But I've got all of them digitized on my computer right now.
Okay, so on this phase diagram, figure 1 here, we have the melting point of ice in glycerol solutions as a function of the concentration of glycerol in the water, and the dark line is the trajectory that might be followed in a standard self-freezing protocol. So you load with 2 glycerol, which corresponds to about 18%, and then you start cooling. Typically in a freezing protocol, you cool on the order of 1 degree a minute, and then temperature will actually go below the freezing point, or aka the melting point, because typically solutions, even pure water itself, will supercool before it actually freezes. So it'll start going down some distance, and then eventually an ice crystal will nucleate, and then the temperature heat will be released, and the temperature will pop back up to become equal to the melting temperature. And then what happens is that as the ice grows, the concentration of glycerol between the ice crystals increases as you continue cooling, and in a standard self-freezing protocol, the concentration of glycerol as the temperature decreases will follow the melting point curve, also called the liquidus curve on this phase diagram. And the way lots of people like to do things in freezing is they'll stop at about -40, the slow cooling, and then just plunge all the way down. Because once you're at -40, you've basically got a practically vitrifiable concentration of cryoprotectant between the ice crystals, and you can do a sort of non-equilibrium vitrification, just plunging. Or what you can do is, if you're patient, you can continue cooling this liquidus curve all the way down, and then eventually you interact with the glass transition temperature, which itself is concentration dependent, but where there's a point where the melting temperature intersects with a glass transition temperature curve called Tg prime, and that is the glass transition temperature in the maximum freeze concentrated solution. So at this concentration here and down here, you've essentially got the conform in a glycerol water solution, and glass transition temperature of the unfrozen solution left. We call that TG prime. And you cool below that. And then you have cryopreservation because you can now store that for practically indefinite periods of time. So that's standard freezing. But there's something else you can do, as I'm sure you all know, and that is if we take this phase diagram and we add on another curve, the homogeneous nucleation temperature, we can look at some different phenomenology here. So the homogeneous nucleation temperature is the temperature below which the solution cannot supercool. So between the ice melting temperature curve TM and TH, freezing is thermodynamically favored, but the size of the ice crystal matters. Just below TM, only very large ice crystals are thermodynamically favored. And that makes it difficult for ice to nucleate because small ice crystals that start forming will melt because they have a high surface energy that makes them easy to melt. And then what happens is you continue cooling, the minimum stable size of an ice crystal gets larger and larger, smaller and smaller, till you get to a point where even a cluster of water molecules, just like 10 nanometers across, would be able to form a stable ice crystal without any substrate to nucleate the ice. And at that point, water homogeneously nucleates. It nucleates without any impurities to nucleate ice formation. The solution itself will just naturally form ice crystals by thermodynamic necessity. And so if you go below TH, you here. So they actually call this, thermodynamicists call this space between TH and TG no man's land, because you just cannot avoid ice in this space. There's sort of one way to avoid ice, and that is if you cool through this so fast that you allow a minimum time for ice crystals to grow, you can vitrify in here. So if you take pure water, for example, and you cool at about 10 million degrees a minute without any cryoprotectant, you can get all the way down to TG and vitrify the pure water, just because you just did not allow enough time for these ice crystals that form to grow. And then there's another flavor of this where you put in just a little bit of cryoprotectant, and then you might only have to cool at 100,000 degrees a minute, and you can still effectively avoid ice crystals, or make ice crystals so small that they're biologically innocuous, which is a whole other subject. And some people call that kinetic vitrification. Basil Lhuillier was fascinated with this regime here, but later on, towards the end of the 20th century, people like Pierre Boutron and then Greg Fay became more interested in what happens at these higher concentrations here. Because if you move up to this concentration range, like in this case above 55 or 60% glycerol, the TH curve intersects with the glass transition curve. And if you load up before you start cooling, you load up with that very large concentration of cryoprotectant and then just cool straight down, you can avoid ice completely by zone. Because recall that in the metastable zone, the only way ice can form is by heterogeneous nucleation by bodies. And that's a kinetic process. It takes time and luck, sort of. It's a kind of a random process. So if you cool through this very quickly, but not as quickly as you have to cool here in kinetic vitrification, but in this metastable zone, you can get a more practical kind of vitrification. And then Greg Fay demonstrated with Bill Rawl in 1985 in their famous Nature paper that they could revive mouse embryos using this technique, and the rest is kind of history. So that's vitrification in this zone. And then there's, well, actually, it's time to move on to another figure.
Well, actually, I have a question.
So,
is it okay if we ask questions
yeah.
after the figures?
Yes, please go ahead.
Okay, so the homogeneous temperature, is there a formal definition of this? Is it like where the critical radius is 10 nanometers, as you said, or is it a soft kind of definition?
It actually comes from something called the Kelvin-Thomson equation, and which relates the critical ice nucleus size to the temperature, and it changes once you get down to the nanometer scale. It changes so fast that it doesn't really matter whether you set that critical threshold at 5 nanometers or 20 nanometers. It's going to probably make less than a degree difference in this pH value anyway. So, but it comes from this Kelvin-Thomson equation, and that's where TH comes from in pure water. Now, things get a bit more complicated once you have cryoprotectants involved in the mix, and there's a kind of empirical relationship that says once you start adding cryoprotectants to pure water, in which the homogeneous nucleation temperature works out to be minus 40. And by the way, there's a bit of randomness in this too. Like, people have done studies with emulsions, which is how you study homogeneous nucleation. Like Zachariasen in particular showed that you can get homogeneous nucleation temperatures as high as minus 30. It's just unlikely, or sometimes maybe even get a bit below minus 40. So this is not an exact hard and fast line the way the melting temperature is. But consider in a few degrees the beginning of no man's ice formation. And then the empirical relationship I'm talking about is it's been found empirically that as you add cryoprotectant, for a 1 degree decrease in the melting point, the homogeneous nucleation temperature decreases by 2 degrees. So for example, once you get out to a melting of 40 degrees, minus 40 degrees, you will have depressed the homogeneous nucleation temperature by 80 degrees. So that's 80 degrees below minus 40, which is about minus 120, which is why you find, and it's only approximate empirical relationship, which is why you find, though, that for most cryoprotectants, a concentration corresponding to a melting point of minus 40 degrees is actually the minimum concentration needed to vitrify. So that's actually why you find that people do things like plunge cooling from a temperature of minus 40 in freezing protocols and things like that, because it's once the melting point of the residual solution reaches minus 40, at that point, the homogeneous nucleation temperature is going to be down near the glass transition temperature, and you're entering the metastable zone. So that's where TH comes from quantitatively.
Makes sense. Thank you.
Okay. Yeah, I have like few questions and things around this. Like, one was that TH, when you have measuring TH, usually, like, that's homogeneous nucleation, which you're referring, but people measuring it with DSC and all, that's like more heterogeneous, because you always have sort of impurities, and that shifts this curve up. Do we
now
much?
Yeah, so you can actually measure true homogeneous nucleation by DSC, and the way it's done is you make an emulsion of the solution. So you mix the solution with certain detergents and then stir it up really good with agitation, and then what you end up creating is a sample that has millions of microscale droplets in it, and most of the droplets statistically are not going to have heterogeneous nucleators in them. So most of you're going to have a large droplet population numerically, because the droplets are so small, that have nothing in them but pure solution. And in that kind of emulsion environment, if you cool in a DSC, it will actually nucleate close to or at the true homogeneous nucleation temperature. So that's how homogeneous nucleation has been studied in DSC and in emulsions, with tiny droplets of solution.
Okay, yeah, that makes good sense. And then the other part was, if you see the TH and the TG interaction, which is happening at about 60 for glycerol, like, do we know what is driving that? Meaning, can we have a CPA which we can have that interaction at 20%, or is there like a physical limit? How much can we shift it towards the left of that?
Yeah,
TH,
so what we find is that solutes that have very strong polar interactions with water, like DMSO, or especially propylene glycol, and most especially mesodepleted 2,3-butane diol, are what we call strong glass formers, meaning they have a very low concentration needed to vitrify. Like with mesodepleted 2,3-butane diol, that intersection happens at almost as low as 30%. So and that solute was discovered by Pierre Boutron, and people were very excited about it in the 1980s. But the reason propylene glycol and 2,3-butane diol fell out of favor is because it became discovered empirically that although physically those solutes that are really good glass formers because they bind water really well, that even though they're physically good for vitrification, they're not biologically good. When you perturb water very strongly by attracting it to the solutes, you then make those water molecules less available to bind to biomolecules like proteins, and you get more toxicity. So it was just empirically discovered that strong glass formers are toxic. So you're actually better off, empirically it was discovered, to use a higher concentration of a weak glass former, even though you need a higher concentration of it, it's actually less toxic to proteins and cells than the lower concentration of the stronger glass former, which is why, for example, Greg Fay in his kidney vitrification work changed from using VS4-1A, which has another name now that I've forgotten, but it's a propylene glycol-based mixture, to an ethylene glycol-based mixture that is M22, or the simplified version being VEG, because EG, even though you need more of it, ethylene glycol, you need more of it, it's less toxic than propylene glycol. So yes, there are some solutes that can vitrify at lower concentrations, but empirically they tend to be more toxic.
Yeah, that is pretty, like, that is a very good balance too, because you will expect to put more like strong glass former at lower concentration, thinking toxicity. And the last thing I was like, if you see that 100% line goes up to like -80 for the TG curve, like theoretically, can we have a CPA which can, like, that TG line can actually go, I don't know, -40, like the curve becomes high at full strength, so you can vitrify it literally like sub-zero temperature as opposed to like cryogenic temperature?
Yes, there are solutes that do that. In fact, they're non-penetrating ones in particular have that property. Polyvinyl pyrrolidone, the polymer, for example, I think has a TG prime at around -30 degrees. But of course it's not penetrating, so it doesn't help you inside cells. But things like sugars, like sucrose, they also have a higher TG prime. But the problem is, if you actually want to stabilize cell interiors, then you usually need penetrating cryoprotectants, and the selection of penetrating cryoprotectants that have a high TG prime temperature is limited. I think I showed back in the 1990s that substituting methoxyl groups for hydroxyl groups on the standard cryoprotectants raises their TG and TG prime. but they also tend to be more toxic. So they're not an option really, at least not in large concentrations. So there are ways to get TG prime up almost as high as you want. The problem is that usually the solutes that do it are non-penetrating.
I guess also, like, maybe we haven't looked enough, like how you say that 1990s replacing the OH. Maybe there are solutes out there which, because it's all empirically DMSO, EG, PG, formamide kind of limited.
Yep. It's actually relevant to food science, because when food companies want their foods to have long life at -20 freezers, and if they're processed foods where they have options to add things, they will actually deliberately look for additives that have a high TG prime to increase freezer the storage time in freezers by keeping things in a more solid state. So people do look at this, but not so much in cryobiology right now. But I think food scientists have spent a lot of time looking at this question.
Yeah, that was when I first came into cryobiology. I mean, one of the example was told to me, like the candy, just sugar candy is a glass which is at room temperature. So I was like, why not form glass of cells and organs at room temperature if we can?
Yeah, if we could get some of those solutes that make the rock candy actually in and out of cells easily, then we could actually preserve cells at room temperature.
Dr. Wowk, I have one question about figure 2, if that's okay.
Yes.
It's usually expressed as percent weight per volume or percent weight per weight here. And I'm just wondering, why is it weight per weight and not molar, in your opinion?
So in the case of these particular graphs, they were what I pulled out of biodynamical. But your broader question is, I guess, why in all the papers of vitrification do people talk about weight percent or weight volume percent so much instead of molar concentration? That is a good question. Let me see if I can think of an answer.
Yeah, because even like when they plot, like critical cooling rates and critical warming rates, it's usually, again, this weight per weight. And it seems like usually they overlap, like the different protectants will overlap around that when you express it as weight per weight. I do freeze drying, and we see that protection is very correlated with weight per volume and not correlated at all with like molar concentration. I'm just trying to understand that aspect a little more.
I can explain that. So what's going on is that at low concentrations of solutes, you have what's called Raoult's law, if I'm pronouncing that right, where you find that at low concentrations, the melting point is depressed by 1.86 degrees Celsius per mole of solute. So basically, that's the linear portion of the beginning of the TM curve here. And you find that it's pretty independent of the solute, actually. And so at low concentrations, it would make sense to plot in terms of moles. But what you find is that once you start getting to higher concentrations, this melting point becomes a non-linear concentration, a non-linear function of the number of moles and even the percent concentration. Because what's happening once you get into concentrations where you are replacing significant portions of the water in the sample, that what matters more is not the number of moles, but how much water you're leaving. So that's why across solutes of vastly different molecular weights, anything even for like ethylene glycol, sucrose, polyethylene glycol, polyvinyl proladone, even things with molecular weight in the tens of thousands. Once you start getting to 10% concentration, 30, 40% concentration, where you're getting rid of half the water in the sample, it's that the amount of water that you're getting rid of matters more than the number of moles. And I think that's the answer to your question. Why do people plot with percent solute instead of moles. And it's because when you look at high concentrations, the behaviors are more similar with looking at percent than looking at the moles.
And do you think that this nonlinear relationship could be, I mean, we've been just like thinking about ideas, like could it be like viscosity or like entanglement or even like bound water fraction is kind of like where we've kind of, that's what we're thinking, but I'm just, you're the expert and I'm just picking the brain.
Viscosity definitely influences where the TG curve is. Offhand, I'm not sure how much it influences the TM curve. That may depend more on other things like the strength of the water interaction with the solute. But of course, the strength of the water interaction with the solute also determines viscosity. So there is an indirect connection, at least, between viscosity and the melting point curve. Not as direct as the behavior of the glass transition, but there's at least an indirect connection.
Thank you.
Okay, moving on to figure 3. There's another way you can do cryopreservation by vitrification, and this is based on an idea that Ferrand and Elford came up with back in 1965, where you add a bit of cryoprotectant and then cool just to the melting point of that concentration of cryoprotectant. You add some more cryoprotectant, which then allows you to cool to a lower temperature without freezing, and so on. So just basically following a pattern of adding CPA, mixing and cooling, adding, mixing and cooling. And those guys, I think, went down to -80, but not below. So what they didn't actually achieve true vitrification, but then later David Pegg used this technique called liquidus tracking to actually vitrify articular cartilage by loading it in the high sub-zero range, always staying above the melting point. And then once you got to a vitrifiable concentration or a near unfreezable concentration, just plunge cooled it and was able to vitrify it. And this it says has advantages and disadvantages to the approach that we're looking at in figure 2. And the Fay approach would be you load up in steps osmotically to tolerate some final concentration of cryoprotectant, then plunge cool. Although, of course, in practice, what we do is not quite this simple, because we actually do cool a bit below zero and actually end loading it when our kidney work, for example, at a temperature of -20 before we plunge cool. But we don't go all the way down to like -40 like the liquidus tracking people do with multiple steps. But if you do, there's theoretically at least an advantage in terms of toxicity avoidance, because the low temperatures mitigate toxicity. So it's a different approach that allows you to modulate that extra variable. So that's liquidus tracking. Oh, and then there's another final technique you can do, which is something that Kelvin Brockbank did to heart valves back in, I remember seeing his presentation in 2007 in Lake Louise, and it raised some eyebrows, at least my eyebrows went up, because he loaded to something like 80% solute concentration for preserving heart valves, and then cooled them. And it's such a high concentration that it qualifies as equilibrium vitrification, because it's an unfreezable concentration of solution. So he was just able to cool that at any speed he wanted. And he could also ship on dry ice. He could park at -80 without fearing ice formation, ship them on dry ice, and then store them below TG for long-term storage. But you could take as much time you wanted within in this higher temperature range and not worry about ice formation. So that's equilibrium vitrification. So both liquidus tracking and going up to a really high concentration and just cooling straight down those are what we call equilibrium vitrification. That's kind of a different thing than what Boutron and Fay were proposing.
Can I ask like couple of things on that? I think the first one on that liquidus tracking method, it seems pretty good approach because, like as he said, reduces toxicity at lower temperature when you're adding higher, and then you don't freeze it at worry about it because you're always above the melting. But I wonder, since the viscosity is increasing more and more, you go lower, the diffusion inside whatever biological thing you are equilibrating will become almost none. So how would you actually permeate CPA at -40 when you're adding it, like, or even -60? That would be like very slow diffusion.
The answer is that, well, first of all, this liquidus tracking method is completely unsuitable for vascular organs because you enter viscosity ranges that are unperfusible. So this is for diffusion cryoprotection, like you do with pieces of cartilage. And the answer to the question is, how do you permeate such viscous concentrations of cryoprotectant? The answer to that is they don't actually permeate. So what happens is once you start getting into the sub-zero temperature ranges, if you're adding higher concentrations of the CPA, you're not actually getting more CPA into the cells. What you're doing is you're osmotically removing water. So for example, if you put in a concentration of CPA at -130 that has a melting point of -40, and you expose cells to that at -30, what's going to happen is water is going to osmotically migrate out of the cells until the inside of the cell takes on the same melting point as the solution that surrounds the cell, because melting point is actually a measure of water activity. So it's a technique for removing water from cells at low temperature that allows you to make the whole thing vitrifiable. And you're actually relying on whatever endogenous solutes are naturally present in the cells, plus the amount of CPA that you got in there in the early stages. Because you do get in some CPA in the early stages, and then as you remove water in the later stages, you're increasing the concentration of the CPA in the cells just by virtue of osmotically removing water from the cells.
Yeah, that is very nice. Yeah, I didn't think about that, water removing. And then on that 80% for the heart wall, does that mean it's like not toxic, or is it just the ECM protection in the heart wall? Like, how can they sustain that high concentration?
Good question. Good question. And the answer is that you can do that cheat with heart valves, because heart valves don't have to have viable cells in them to function as heart valves. Basically, when you cryopreserve heart valves, you're cryopreserving the extracellular matrix, the fibers that surround the cells in the valve. And heart valves, transplanted heart valves, actually do okay clinically, even if all the cells in them have been killed. Sometimes some workers have even said that's advantageous for avoiding rejection. So it's kind of like the 80% CPA serves the dual function of giving you a nice unfreezable sample and also making it less antigenic by wiping out the cells by toxicity.
That is very smart. Yeah, wow. Thank you.
Okay. So now we get into some interesting thermodynamics. So imagine that you take a piece of crystalline glycerol. Pure glycerol does form crystals. In fact, back when I lived in Winnipeg, a climate like Minneapolis, one time I had a bottle of glycerol from a pharmacy, and it had been in my car in the wintertime, and it had actually solidified. So I'm wondering, what is going on? How is this solid? I thought glycerol was a liquid, but actually the freezing point of pure glycerol is plus 18 degrees Celsius. So it's almost room temperature. And the reason we rarely see solidified glycerol is because it has a strong tendency to supercool. So you could usually like even put it in the refrigerator and it won't freeze. It takes a lot to nucleate it, but the actual technical temperature at which pure glycerol crystallizes or crystallization is thermodynamically favored is plus 18 degrees Celsius. So let's say we take a piece of crystalline glycerol and we have it down at absolute zero. And then we start adding heat to it. And we carefully measure the amount of heat we're adding to it and the temperature, the amount that the temperature rises as we add heat. And we get this curve here on the bottom of figure 5, which reminds me, how are we at figure 5? Did I miss figure 4? Oh, figure 4 comes later anyway. Okay, so imagine that we're adding heat and we're observing this crystal of glycerol warming up, and this is basically the integrated amount of heat that we've put into it to get up towards its melting point. And then as we keep adding heat, the temperature stops rising because that heat now is melting the crystal to make liquid glycerol. So now we've got a sample of liquid glycerol right at the melting temperature. And now we're going to start cooling that liquid and measuring the amount of heat we take away from it. And we're going to do this fast enough that we're going to vitrify the glycerol, and we're going to supercool it and then vitrify it without letting it crystallize. So we're taking heat away, and you'll notice that this curve has a steeper slope on cooling than the slope on heating. It's because liquid has a higher heat capacity than a crystalline solid. So we're taking away heat, and then there's a change in slope where from now on, as we take away heat, we're taking away less heat to get a given amount of cooling because the heat capacity is changed. So that bend in the heat curve there is actually a glass transition. So here we're supercooled liquid, and here we're a glass. And as we keep taking heat away from glass, we actually find that you can get all the way to absolute zero, and you still have some heat left. There's still some energy left in that glass. So that's a basic difference between a glass and a crystal. A glass is in an intrinsically higher energy state than the crystal. The molecules are. Go on.
Yeah, and that energy is purely to do with the configuration, correct? Like it doesn't reflect some sort of molecular motion close to absolute zero or something like that.
No, what it reflects is that the molecules are basically farther away from each other in the, well, we got to watch out for that because water expands when it freezes. The hydrogen bonds are weaker in the disordered liquid state than they are in the crystalline state. So in the crystalline state, the hydrogen bonds are in a deeper potential well. The oxygens, there's more oxygens and hydrogens that are closer to each other in tight hydrogen bonds in a crystal than in the disordered liquid. So yes, you're right. It's not vibrational. It's a configurational difference in energy, that there's not as many organized tight hydrogen bonds in the liquid or glass state as there is in the crystal state. So there's another thing we can do here, which is if as we build this graph in figure 5, we divide the heat flow by the temperature as we go, then what we're actually doing then is we're making a plot of the specific entropy as we go, because entropy is being defined by heat flow divided by temperature. And so then what you find is, in the case of the crystal starting from absolute zero, the entropy increases, and then in the case of liquid, of course, the liquid has a higher entropy than the crystal, and the entropy of the liquid decreases faster with cooling than the crystal does, until you get to that bend where you get glass formation, and then from then on, the slope of entropy decrease of the glass is the same as the crystal, but you still end up at absolute zero with more entropy than the crystal. And that's another way of saying that there's more ways to organize the glycerol molecules, in this case, in the form of a liquid than there is in the form of a crystal. A crystal is a very specific structure, whereas a liquid is much more random with a much larger space of possibilities of molecular configurations corresponding to the same macroscopic thermodynamic variables. And then if we take the this curve here that we looked at previously, this integrated enthalpy or flow curve slope of these lines, then we can actually make a graph of heat capacity. And what you find is that the liquid in the supercooled liquid has a higher heat capacity than the crystal, and then you get a glass transition, and then once you've glass transitioned, the heat capacity of the glass and crystal are practically the same. And this is starting to look a lot like a DSC curve, because as we all know, what DSC curves at a constant warming or cooling rate are plotting are changes in heat capacity. So that's the story of that curve. So let's see, what other interesting stuff do we got going on here? So there's something very interesting about the glass transition, and it's the non-equilibrium nature and the observer dependence of the glass transition. And to emphasize the observer dependence, I'm going to look at it here. Where is that plot? No, sorry, it must be further up. No, it's not there. Yeah, okay, this is the one I want. Fine. Say you do a DSC experiment, and well, this is actually this is integrated heat capacity, or actually this is entropy, but same concept pertains that if you cool fast, you'll measure a higher glass transition temperature than if you cool slowly. So the glass transition temperature you measure actually depends on your cooling rate. And this is why the glass transition is not actually a formal thermodynamic phase transition, because the definition of a thermodynamic phase transition is a transition between two equilibrium thermodynamic states. But a glass is not actually an equilibrium state, because what happens is that as you're cooling, these molecules are moving around, and they're configurationally trying to figure out different ways to give up heat. And but as viscosity increases, it gets harder and harder for them to give up, to find ways that are to find configurations that are lower energy that allows them to give up more heat. And what happens as you continue cooling is eventually they sort of give up trying to explore their configuration space to give you more heat. And they just say, if they were thinking beings, it's getting too hard to move around in this room. I give up, Mr. Scientist. I'm not going to put more heat into your DSC because it's just too hard to move around here. So I'm just going to stay where I am. Even though I know that there are other places I can go in this room that would be lower energy states, and I could give up more heat. I'm going to stop doing it right now because it's just too hard to move around amongst all these viscous neighbors of mine at this temperature. But if you actually continue holding at a temperature below where Mr. Water molecule gave up giving you more energy, and you wait long enough, the water molecules and cryoprotectant molecules will actually slowly wander around and find ways to give up more energy, to decrease their volume and decrease their entropy. And they can actually lower their own glass transition temperature over time if you wait long enough. And that's why if you cool more slowly, you can actually measure a lower glass transition temperature, because you get to a lower temperature before the water molecules finally give up trying to find different configurations. And so this is why the glass transition temperature is a kinetic phenomenon, and glasses are intrinsically not at thermodynamic equilibrium. And if you wait long enough, even holding a constant temperature below the glass transition, they will continue to relax. And there is in glass science what's called a relaxation time, or a characteristic relaxation time. Let me just find the equation for that here. And this applies to a whole bunch of different, equation 10 here, this applies to a whole bunch of different physical parameters. This pertains to things like dielectric relaxation, density, heat capacity, basically compressibility, all the thermodynamic response functions. If you wait long enough at a given temperature, they will move towards an equilibrium value. And the speed at which, and they will do so exponentially or approximately exponentially, and the speed at which they will move towards their equilibrium value is called the relaxation time. And it actually turns out, this is the most interesting part I'm building up to say, and that is, with the way glass transition temperatures are usually measured in the laboratory by cooling on the order of 1 degree a minute, what you find is that the glass transition, as typically defined by that laboratory measurement, corresponds to a relaxation time of about 100 seconds for all those different parameters: dielectric relaxation, heat capacity, physical density. There, if you stop cooling right at the laboratory measured glass transition, those things will, those parameters will continue relaxing with a time constant of about 100 seconds. And this is intrinsically related to our human time scale and the patience of an investigator. Because like if we lived on another planet where people did things slower, like say 100 times slower than we usually do, so scientists were more patient, they would actually be publishing glass transition temperatures of their solutions that were probably about 5 degrees lower than ours, just because they were more patient. So that's an interesting thing about glasses, is that they are intrinsically a non-equilibrium state. But the further you cool below the glass transition temperature, the less relevant that becomes, except for theoretical reasons. It's mostly of interest to theorists. Like at liquid nitrogen temperature, the relaxation time is going to be negligibly long, or at minus 150, the relaxation time is going to be negligibly long.
Yeah, so I was going to ask here about the aging of glass, which you have. Like, how, what would be an age? Like, you know, we say vitrified state at certain temperature, you know, store it forever, but like how long will it take for glasses to actually age, basically like go to their equilibrium state from the non-equilibrium?
Well, it's based on this equation here. The Kohlrausch-Williams-Watts function, and then the relaxation time tau. But then you're going to ask, how does the relaxation time tau vary? And I believe the answer is that tau itself has an Arrhenius dependence. So just to give
like
you a sense, just to give you a sense of this, people storing 10 degrees below the glass transition temperature, for example, have found aging to occur over a period of years. And the way it manifests actually is in an enthalpy overshoot when you warm back up again. Because remember how I was saying what aging of glass really means is these water molecules finding ways to get to a lower configurational entropy and enthalpy. So if you wait a long time and you're close enough to a glass transition, they will eventually settle down into a lower energy state. And the main consequence of that is that as you warm them back up again and you go through a glass transition, you'll actually get an enthalpy overshoot on the DSC. And people have actually done this. Like they've taken DSC samples that have been stored for years, like 10 degrees below the glass transition temperature, and then warm them back up again, and you find you get a big enthalpy overshoot, meaning that that sample, the glass in that sample is actually relaxed over that time period of years. But this is mostly of theoretical relevance. The aging of glass, actually the main thing that the aging glass is going to affect is thermomechanical stress, because thermomechanical stress will relax on the same time scale as the other glass relaxation that we're talking about. So you'll get a relaxation of thermomechanical stress. In that sense, the aging is actually a good thing. Offhand, I can't think of anything cryobiologically bad about the aging of glass. In a minute, we'll talk about ice nucleation, but that's completely different. That's unrelated to the subject of glass aging.
Yeah, I asked that because, like, there's this myth around, or not myth, but like some reality about like these middle-aged churches having windows which are thicker at bottom because glass actually flew, like not, but like glass flow and they become thicker. So it was like, over 500 years of a glass, if you leave it, it's actually can change, physically shrink or swell and things like that. So I wonder if a vitrified organ like can change in 500 years, shrink or become.
If you store it 10 degrees below the glass transition, maybe even 20 degrees below the glass transition, it will change over 500 years. It'll become like maybe 1% smaller, and it maybe give up like a couple of percent of its enthalpy, and thermomechanically relax. So if you're just like relatively close, and by relatively close, I mean 10, 20 degrees of glass transition, the glass will relax over years and centuries, but it's not, I can't think of any cryobiological significance to that other than the benefit of having less thermomechanical stress. But in the case of the window glasses, that's a myth, because window glass is hundreds of degrees below its glass transition temperature. So there is no relaxation going on there over centuries. And when window glass is narrower on one end than the other, it's because it was made that way, and it's always been that way. So yeah, the window glass does not undergo relaxation over centuries, but cryoprotectant glasses 10 or 20 degrees below the glass transition would. Down at liquid nitrogen temperature, not so much. I mean, when you're 60, 70 degrees below the glass transition temperature, relaxation would not be significant even over centuries.
And you probably all know this, but I think I heard that the window glass phenomenon was that for some reason it's easier to install with the thicker side down. So they installed it that way from the start.
Yeah. Now, since we're getting close to the end of our hour, I will move on to something that is a cryobiological concern, and that is ice nucleation. There's a lot of literature if you look for it, and the AI engines that are available now can easily help you find this literature. You can have a conversation with AI these days about this whole subject, just like just about any subject. But there's literature showing that ice nucleation proceeds rapidly near the glass transition temperature. Not ice growth. The viscosity is so high near the glass transition temperature that ice can't grow, but ice nucleation happens like crazy near the glass transition temperature. And in fact, in the solutions that are favored for organ vitrification in work that people like Patrick Mell have done, and that I did, at least as an abstract back in 2007. I still need to publish this properly. We found the ice nucleation rate in organ vitrification solution is actually maximal at the glass transition temperature, and continues for at least 10 degrees below the laboratory measured glass transition temperature. And I'm not quite sure where it stops, but I think to be safe, you need to be at least 15 to store at least 15 degrees below the glass transition temperature, probably even colder. And so you have this kind of tension in the field of organ vitrification between thermomechanical stress concerns and ice nucleation concerns. For ice nucleation reasons, you want to store as cold as you can. For thermomechanical stress reasons, you have to be really careful once you go below the glass transition temperature. I mean, it would be ideal to store in liquid nitrogen, but you have to cool really, really carefully to get an organ down to liquid nitrogen temperature without fracturing it. Probably minus 140, minus 150 is okay for years of storage, but this is really an understudied area. This is just screaming for more DSC research, but I just have been too distracted by other things. But this whole question of what is safe temperature to store vitrified material at is an important question.
Yeah, this is like, as you say, this is a very interesting thing which people have overlooked, and they usually just do the CCR, CWR, and like instead of going to nucleation rate and growth rate. And one of the thing I was thinking is like, as we change this concentration, do these two curves move together, or does the valley between them closes off? Because in pure water, you don't have a valley. They're overlapping.
Good question. And Hay and McFarland published papers at intermediate concentrations of vitrification solution, and they compiled time temperature transformation curves that effectively mapped ice nucleation and melting curves. And what they found is that at low concentrations, like vitrification solutions you'd use for reproductive cryobiology, for example, these curves do overlap. It's at the high concentrations used for organ vitrification that the curves separate, and you can actually get a valley between these two zones of ice growth and nucleation, which is convenient for doing the measurements. So it's actually easier to separately measure ice growth and nucleation in these concentrated vitrification solutions than it is in the more dilute ones. But yes, the curves do separate at high concentrations.
Thank you.
Would there be any way to take, or would there be any benefit to, like, could you make use of this trough in some way for, I mean, probably annealing doesn't really matter because there isn't that much stress at that point, but you have this pause window, right, where you could spend some time in the minus 90 or something.
Yeah, I sometimes think that you could almost use this for shipping organs. If you perfused an organ with a vitrification solution and you cooled it rapidly to dry ice temperature, you might almost get away with shipping it to a long-term storage facility that had a lower temperature. But I worry, though, that as a practical matter, cryoprotectant toxicity would probably kill you, even if you could avoid the ice growth because you haven't nucleated much yet. The toxicity would probably get you. So yeah, I'm not sure how practical it is to use that valley.
Thanks. Makes sense.
So we're at the 1 hour mark. I could go on about other topics on this paper, things like chemical reaction rates as a function of temperature, if you wanted me to, or we could stop right here, or I could take more questions. Just tell me what you'd want to do.
I think, I mean, if people got to go, they please feel free to leave. But I think if you have time, Dr. Wowk, I mean, we could spend a couple more minutes if that's okay.
Okay. So the issue of chemical reaction rates is kind of interesting because it's so different from the ice nucleation situation. let me go and find the Stokes-Einstein equation. So the Stokes-Einstein equation, equation 15 here in the paper, relates the diffusion coefficient to the viscosity of the solution, and which in turn can be converted into a distance, a mean distance diffused as a function of time, which is what the diffusion coefficient relates to. So some years ago, what Greg Fay did is he plugged in the viscosity of a vitrification solution, or more accurately, of a cryoprotectant solution for vitrification as a function of temperature using the VFT equation. And the VFT equation is mentioned elsewhere in this paper. It's a standard relation between temperature and viscosity of supercooled solutions. So use the VFT equation to calculate the viscosity of M22, a vitrification solution, as a function of temperature, and then plugged it into the Stokes-Einstein relation. And on that basis, assuming that chemical reaction rates would be proportional to diffusion time, so that this ignores like the Arrhenius dependence of chemical reaction rates on temperature, which depends on the activation energy of specific reactions. The Arrhenius equation would actually predict a slowdown of chemical reactions that would be on top of the slowdown due to viscosity changes, because the viscosity is what determines the ability of reactants to reach each other through the solution. And then the Arrhenius equation, once the reactants are in contact, determines whether they have enough thermal energy to overcome the activation energy for the reaction to make the reaction happen. So what Greg looked at is he just looked at the question of what happens to the rate at which reactants can move together in a vitrification solution as a function of temperature. And what he found is that in M22, 1 day at minus 80 degrees is equivalent to 1 year at minus 100 degrees, and then equivalent to thousands of years at minus 120 degrees. So even if we reduce that by 1 order of magnitude or 2 orders of magnitude, so we're talking about minutes, say, which is probably in hindsight how I should have written this, that like one minute at minus 80 would probably be like 1 week at minus 100, and then centuries at minus 120. So the moral of the story is that the standard theoretical prediction for the ability of chemical reactions to proceed at these low temperatures that vitrified materials are stored at is negligible. The main concern seems to be ice nucleation, which, as we've seen, proceeds much faster. But we don't seem to need to worry much about chemistry below the glass transition temperature. Having said that, as I mentioned in this paper, there are some empirical results that I think seed preservation people have looked at this in particular, showing time-dependent degradation of seeds stored in liquid nitrogen vapor at minus 150 over periods of years. And the mechanism for this is not well understood yet. But if I had to guess, it would be something like the viscosity predicted by the VFT equation is an overall solution viscosity. And if your solution consists of a combination of water and high molecular weight things, and the high molecular weight things are what's creating most of the viscosity. The water molecules themselves are actually going to be more mobile than this VFT Stokes-Einstein formalism predicts, because the viscosity is like a global thing that includes both water and the polymers, but the water itself may actually be more mobile. So what might actually be happening in these seed results is the seeds, which have a relatively high surface area to volume ratio, might be dehydrating over a period of many years due to residual vapor pressure, perhaps, at that temperature. But it just shows you have to be careful in applying these theoretical models, because their underlying assumptions may not apply in all cases. Okay, any remaining questions?
Oh, this last part was really interesting. Like, thank you for, because people might take it as, like, storing a TG is samples would be good forever kind of mentality, but that may not be true.
Yeah, models have their limits. Models are limited by their assumptions.
So I'm wondering, there's a thing where you talk about the Kautzmann temperature, and I don't fully understand, but it says the Kautzmann temperature, the temperature at which the entropy of a liquid that remains in thermodynamic equilibrium during slow cooling is extrapolated to fall to the same entropy as a crystal. So on a practical basis, would it be reasonable, that's top of page 18, by the way, would it be reasonable to think of it empirically as some safe temperature for storage, seeing as you get that, paradoxical intersection?
As a practical matter, the Kautzmann temperature is so much lower than the glass transition temperature, like typically 20 or 30 degrees below it, that you're probably safe at that temperature, even against ice nucleation. But that, I think that's kind of a coincidence. I don't think the theory of the Kautzmann temperature or the Kautzmann paradox is what confers that stability. And I just brought up this graph to explain what the Kautzmann temperature is, because it's kind of a subtle thing. So if we look at this specific entropy graph here, and we're looking at the supercooled liquid, if you take this supercooled liquid and you extrapolate this line of the entropy of with this slope of the entropy of the supercooled liquid until it intersects the crystal, then that would be the Kautzmann temperature. So basically, the Kautzmann temperature is what you get if you took forever to let a glass to relax. It would eventually, it would be extrapolated to reach the same entropy as a crystal. And the Kautzmann paradox is that if you waited longer, then naively, the entropy could even become less than the crystal, which is physically impossible. So yeah, people have come up with different theories for what avoids the Kautzmann paradox or the Kautzmann catastrophe, but it's not of much practical relevance, because the amounts of time that you need to wait for the glass to relax enough to get close to the Kautzmann entropy is like probably longer than the lifetime of the universe. So it's mostly of theoretical interest. But yeah, just precisely because of that, because relaxation is so slow near the Kautzmann temperature, I think you're right. As a practical matter, storing at or below the Kautzmann temperature is safe, probably even from ice nucleation as a practical matter. Yes.
Yeah, because that's a common question that comes up, okay, so 10 below TG is not enough, 15 below might be, like, where's the line, right? Where are you truly safe? And I don't know if there's a hard line to speak of.
Well, again, I don't think glass relaxation per se is a bad thing. It's actually a good thing to the extent that it relieves thermomechanical stress. I do worry about ice nucleation, which is a separate phenomenon from the glass aging itself. And I just really like to see more DSC study there. If I live long enough before I retire, I hope to do it someday if no one else does. Because what may actually happen is that nucleation is expected to be heterogeneous, because the organ vitrification solutions are so concentrated that the homogeneous nucleation temperature is way below the glass transition temperature in organ vitrification solutions. So all that nucleation is going on. It's got to be heterogeneous, which means that it may be time limited. Like if you wait long enough, you may just find that it maxes out once you've exhausted your population of heterogeneous nucleators. I don't think it's going to go on without limit, but I would just like to see some DSC data.
Thank you, Dr. Wowk. That was great, and we really appreciate having you at our Meet the Authors series, Journal Club series for ICYR. Sorry we went a little bit over, everybody, but I think that's always the best part. We can kind of just sit around and talk science for as long as we want. So thank you. I hope everyone has a great day, and we hope to see you at the next one.
Bye, guys. Thanks for the invite.
Thank you.
Yes,
Thank
thanks
you.
again.
Fantastic.
Bye.
Thank you.